start the recording here. Okay, so we are in section 4.3. We are using calculus to help us graph functions. And naturally, finding out where these functions, these nonlinear functions, increase or decrease, finding out where the functions are concave up or concave down, gives us a lot of information to accurately graph the function. So what I have here is yet another example. And let me give you a moment to copy that example down. Okay, so our function is y equals x squared divided by the quantity x minus 2 squared. This is a rational function, and you'll have a problem similar to this in your homework for section 4.3. So I didn't want to do the entire problem. You know, I'm only doing the part where where's the function increasing, because I want you to be comfortable with that, and then I think you'd be able to work through the concavity part. So, okay, to find out where the function, and I should say here, there is a correction. There is a correction here. Find out where the function is increasing and also decreasing, right? So let's add that to our notes. Okay, find out where the function is increasing and decreasing. Let me correct that in my notes here as well. So how do we determine this? How do we determine where a function is increasing and decreasing? We're going to resist the urge, by the way, to graph this on our calculators. We're going to use calculus to help us graph the function. Okay, that's right, Joe. We got to find the derivative of y. We got to find y prime. All right, first derivative. So let's go and move forward on that. Okay, so here's our function. And I'm going to use the quotient rule. I'm going to use the quotient rule here to get that first derivative. So sometimes when I do a problem, I think about what's the best way to take my derivative, and oftentimes I don't like to use the quotient rule, But in this case, it's going to be like if I were to write the function, as x squared times x minus 2 to the negative second. Okay, and use the product rule. I would still, when you use the product rule, you get two pieces, and you have to then combine them, and you'll be combining two fractions, and that's okay. Sometimes that's the best way to go. We saw a problem like that. But in this case, I'm just going to use the quotient rule straight. Now, at this stage here, I've used the quotient rule, and I'm going to just then write the first derivative this way. Okay, and let me know if you have any questions. Okay, so here we are. So let's pretend you're doing your homework. Okay, or let even better yet, I mean, let's pretend it's the next exam, and you know I'm going to look at your work. What must you? So you want to do your homework like you're doing the exam, right? So what do you do here? What must you do? I mean, we know we want to produce a chart. Okay, we want to produce a chart to determine where that first derivative, f prime of x, where it's positive and where it's negative. And right now, I have my first derivative written this way. So what must you do next to get that chart? Well, of course, Joe, we're interested where the first derivative equals 0, but even to determine that, I mean, can I easily work with this expression here? Can I easily work with that? Is there something I could do to make that expression better? That's right, Betsu, a factor. Factor. Okay? We are going to factor that. So we're going to factor the numerator. And here are my two terms in the numerator. What is my least common denominator? Or I should say not least common denominator, but least common factor. Let me try that again. I mean, what's the common factor? What's the common factor between these two terms? Two times x minus 2. That's right. Well, John, x minus 2, but also you have a 2x. So if you think about it, you have like the 2x squared. I don't know if you remember doing this, but like 2x squared you can write as, hold on here. This might help. I mean, I just sort of thought of this, but I remember when I taught like more fundamental math, that this is what they did. So what I'm doing is I'm writing out the term in factored form. So in order for this to work, you have to find the greatest common factor, right? So I've written each term out in the factored form. And what I do is I say, okay, well, they each have a 2. They each have an x. And each of them has an x minus 2, 1x minus 2. And so that means that your greatest common factor is 2x times x minus 2. I mean, that is your greatest common factor. That's your GCF. How many remember doing this kind of thing, maybe in intermediate algebra, to determine the greatest common factor? Okay, but Sue remembers it. Nicholas, okay, way back, John remembers it, Joe remembers it. So you've done it before. Well, that's what you do. That's what you do. And so now, what's left then? What's left is, of course, x minus 2 here minus this x here. And x minus 2 minus x gives you negative 2. Are there any questions so far up to this step? All right. Another thing that's sort of nice is we have everything's being multiplied, everything's factored. We have an x minus 2 here, and we have an x minus 2 to the 4th in the denominator, so that would become x minus 2 cubed. And so this is your answer. This is what f prime of x is. So it takes a little patience, but it is very doable. It is very doable. Okay. See, I'm focusing on this because on your exam 4, these kind of problems, I'm going to need, I'm supposed to test you on your understanding of the calculus concepts. So I'm going to need to see this work in order for you to get credit for these problems. And I just want to be sure that you're comfortable. Oh, where's the negative 2, John? Okay, negative 2. I took the 2 here and multiplied it by this negative 2, and that got me negative 4. Are there any questions? Okay, well then let's proceed on. Let's proceed on. Now we're ready to make a chart. And in our problem here, we have 1, 2, 3 components of that first derivative. That's what goes in the chart. Okay. Now, when we look at this first derivative, naturally, as I think Joe had mentioned, we want to know where the first derivative equals 0. Well, clearly it equals 0 when x is 0. So when I make the x-axis here, okay, I'm gonna definitely include 0. 0 is one of my interesting values. Another interesting value is x equals 2, because that's going to make the denominator non-zero, and it's going to make it 0. And actually, what I might mention here, probably should have done this in the beginning, but I always like to identify the domain when I work a problem, like right away. It's usually a good idea to identify the domain, and the domain here is going to be, of course, it's going to be all real numbers except x equals 2. What happens, by the way, at x equals 2 for this rational function? What's going to be there at x equals 2? A vertical asymptote. That's right, Zoe. So it's sort of like I want to use sort of common sense thinking to move me forward. So now that the domain, clearly x equals 2 is a vertical asymptote, and then that makes sense then relative to the chart, because the first derivative here is not defined at x equals 2. Why is that, by the way? Why is the first derivative not defined at x equals 2? Because you have an asymptote there. Well, that's right, Joe. So the derivative, there's a vertical tangent. Well, I want to be careful here. The derivative does not exist at x equals 2. Yeah, that's exactly right. Not defined. Right. That's right. Very good, Joe. Joe's looking at the first derivative. First derivative is not defined at x equals 2. So okay. Now what we do is we write down our factors. We have our 4 factors. Okay, we have our 4 beautiful factors here. -4 is always negative for any x value. Positive x would be positive when x is greater than 0 and negative when x is less than 0. And x minus 2 cubed, well, we know that factor is going to equal 0 when x equals 2. And certainly it'll be positive when x is greater than 2. But it'll be negative when x is less than 2. Because, like, if you had, say, like 1 minus 2 cubed, it's cubed, right? It's an odd power. So that's going to be -1 cubed, which is equal to -1. Okay, so now we can determine the sign of our derivative based on the chart. And just so I'll sleep better knowing this, why do I have negatives here? Why is the first derivative negative when x is less than 0? How am I getting that from the chart here? How am I getting that? How am I getting that? Okay, a negative times a negative, then what? Good, divided by a negative. Good, you got the general idea. Okay, and then of course for this part here, we have when x is between 0 and 2, we have a negative divided by positive. No, a negative times a positive divided by a negative. That gets us a positive. And you know how this works. And so now, because our first derivative is negative on the intervals -infinity to 0 and 2 to infinity, the function's decreasing there. And because our first derivative is positive, okay, positive from 0 to 2, the function's increasing on that interval. And we note that there's a vertical asymptote at x equals 2. So what I'm trying to do is I'm trying to do enough of, and I believe this is my 5th example from relating to section 4.3. I'm trying to do enough examples with you so that you can hopefully handle any problem you see in the homework. I mean, you're going to see new functions, new problems that you have to make charts for, but you ought to be able to hopefully be able to comfortably handle it. It may not be entirely comfortable, but you ought to be able to, with a little bit of patience and a little bit of thinking, get it. All right, are there any questions at all? For concavity, of course, we would then we would find the second derivative. Obviously, you know that there's going to be finding a greatest common factor involved in the numerator, factoring out the numerator, and I mean, you know how this is going to work. All right, are there any questions on that problem? I want to do one more from section 4.3. I want to do one more with you. Okay. May we move to the next problem? Has everybody had a chance to copy the notes okay? All right, Joe's good. Okay, well then let's move forward. Okay, Rodrigo's good, very good. Okay. Well, so I want to do another problem with you that is, and this is a curve. Well, let me give you a moment to copy down this example. Okay, so here's an example of a function that you've probably never graphed anything, and you've probably never seen anything like that before in your previous courses in terms of graphing a function like this. Y equals the log of 1 minus the log of x. Okay, so, and again, calculus allows us to, from pre-calculus, you have an idea, like, for instance, on rational functions, how to find horizontal asymptotes, vertical asymptotes, oblique asymptotes. You have an idea about, like, for polynomials, how to, how to do some things with that. But calculus allows you to be able to graph a wider variety of functions. And here's one right here. Okay, so y equals the log of 1 minus, y equals the log of the quantity 1 minus the log of x. So we want to find concavity, points of inflection, local maxima, minima, use the information to sketch the curve. Okay, so of course, now what might be a good thing to find on this function? What might be a good thing to determine on this particular function? Before we even take the first derivative. Okay, good. The domain. Good, Nicholas. Good, Betsua. The domain, where the function is defined. That's right. So, okay. Well, what's gonna dictate where the function's defined? Okay, good, Ian. So the key is we're taking the log of a function. This function, this function, in order for my function y to be defined, 1 minus the log of x has to be what? 1 minus the log of x needs to be positive. That's right, Kelvin. Very good. So, all right, let's start there. Well, it just needs to be positive, Nicholas. Just needs to be positive. So, okay. So, all right. The domain, I don't know what the values of x are in the domain, but I know that 1 minus the log of x, for this function to be defined, 1 minus the log of x has to be greater than 0, which means 1 is greater than the log of x. And then if we exponentiate both sides of this inequality, we'll get e to the first is greater than e to the log of x. So that's just exponentiation. It doesn't change the inequality sign. Dividing by negative or multiplying by negative would change the inequality sign, but not exponentiation. So e to the log of x is just equal to x. So that means e is greater than x, but you're probably used to seeing it as x is less than e, and therefore 0e is your domain. That's your domain. So this function here, make that a little bit nicer here. This function is not defined, it has a limited domain, 0 to e, and e is about 2.7. Okay, so now that I know the domain, I'm ready to take the first derivative. Okay, and what rule did I use? What rule did we use here? to take the first derivative. That's right. So we use the chain rule. We use the chain rule. And we know the derivative of the log of a log function, the derivative of the log of x is 1 over x. So the derivative of the log of 1 minus the log of x is 1 over 1 minus the log of x. But then we have to take the derivative of that 1 minus the log of x, right? That's your inner function. And that's just going to be negative 1 over x. So we, in factored form, the first derivative equals negative 1 divided by x times 1 minus the log of x. Okay, and that's in good form. Now we're ready to make our chart. See, it's like this. I don't care what the function is or what your derivative is. It's the same. We do this. You know, consistency helps us be comfortable. We have this derivative in factored form. There are 3 components to the derivative: the negative 1, the x, and the 1 minus the log of x. And so we're going to just go ahead and create a chart based off of those components. Are there any questions, at least so up to here? Are there any questions? Okay, good, good. So, all right. So here's my axis. Okay, my domain. I mean, really what I'm drawing here is my domain, right? I mean, that's what I'm drawing. And the domain goes from 0 to e, but doesn't include the endpoints. And now I put each factor down, or each component. Negative 1 is always negative. Positive x over the interval from 0 to e would always be positive. And 1 minus the log of x also would always be positive from 0 to e. I mean, at the greatest value e, what's the log of e equal to? If you were to compute, you know, 1 minus log of e, good, Sebastian. The log of e is 1, so 1 minus 1 is 0. But then anything less than, like x less than e, you're gonna get like if you had the log of a half e, let me see here, you would get a value less than 0. So what I'm trying to say is 1 minus the log of x is positive from 0 to e. And so the first derivative then, okay, which is equal to the negative, well, all right, so the first derivative is negative everywhere here, right? How are they determining that just from the table? How are they determining that? How are we getting that it's negative based off of your components? Good, good, Sebastian. We're taking a negative and we're dividing it by a positive times a positive. Absolutely. And that's going to be negative. And therefore, this function is just decreasing over the interval from 0 to e. The function is decreasing. There's no local maxima, there's no local minima. Okay? It's just decreasing. Now, the absolute min and absolute max would occur at the endpoints, right? The absolute max of the function would occur, well, I got to be a little bit careful here because 0 and e are not included. So we got to be careful on that. I don't want to say that because they're not included in the in the function. But at any rate, are there any questions so far? Okay. What's next? What's next? What do we need to do next? Concavity. That's right, Joe. And for concavity, we need to work with the second derivative. Okay. And so I'll go to the next page, but is everybody comfortable here? I want to make sure I'm pacing myself well. Okay. All right, Nicholas, very good. Well, then let's go to the next page. Okay, and so here we are. Now, I did this problem. When I did this problem, I mean, I really worked it like a student would work it. Okay, and the first time, well, of course, here's your derivative. The first time I worked the problem, I took the derivative of, to get the second derivative, I took the derivative of the first derivative, naturally, in this form as a fraction. But I didn't like what I was seeing. It was getting too messy. It's getting too messy. And so I said, let me not continue on this path. Let me write the first derivative as a product. So, the first derivative as a product would be negative times x to the negative first times 1 minus log of x to the negative first power. And then I use the product rule. Now this negative in front, I just kept it in front. Okay, and then I use the product rule where my two functions are as shown here. Okay, so a lot of derivatives going on there, but you're using, what are we using here? To get our to get our answer here. What rules did we use? We used the product rule, and then we had the derivative of x to the negative first. That's the power rule. We use the chain rule to take the derivative of 1 minus the log of x to the negative first. Okay, and we had to take the derivative of a log, right? So a lot of different rules here. But if you do it right, it will work out. It will work out. Are there any questions here? All right, Betsu is good. All right, and everybody's concentrating, and that's excellent. We do have a few students out today, but they're not working on the exam now because I deactivated it. I don't think it's right that students work on the exam during class time. I mean, you're here learning, and you're not working on the exam. You're learning, you're participating. So I don't, I like to be sure that I like to show respect, All right, so okay, so I have all these negative exponents, so I rewrite the second derivative as you see here. Okay, are there any questions so far? All right, well, we have the sum of two fractions. When we have two fractions, what do we like to do with those two fractions? Add them, combine them, absolutely. We want to combine the fractions. And that means we need a least common denominator. We need a least common denominator. So what I'm going to do is I'm gonna distribute the minus through, if that's all right. And just, here I have an x and an x, that's x squared. So, here we are. And what is the least common denominator here between these two fractions? Okay, so let me just, so LCD. That's right. That's right, Joe. It's x squared times 1 minus log of x quantity squared. See, the 1 minus the log of x, you got to have a square. You got to have a square there because that's the highest power. You have a power of 1 here, but you have a square there. So, okay, I'll multiply then the first expression by 1 minus the log of x over 1 minus the log of x. Okay. And then the second expression just stays, that already has the common denominator there. And now I can combine the expressions. I can combine the fractions to get me this here. Get me this result. Turns out something nice happens. Okay, turns out something nice happens here. Let me just write this. Write the second derivative there. So naturally, those ones, they cancel out. And now you're left on. There is a negative here. Okay, you're left then with this expression as your second derivative. It looks, and it's in, basically simplified factored form. So the second derivative is -1 times the log of x divided by the expression x squared times 1 minus log of x squared. Is it time to make a chart? You know, for your next exam, exam 4, I want to see charts. But actually, exam 3, your exam right now, you have a problem in section 4.3, a polynomial, but I'll need to see a chart for that too, right? So, okay, looks like we have 4 components. Four components to the second derivative. Let's go ahead and make the chart. Are we ready? Are there any questions? Okay, well, let's move on then. Thank you. So here's the second derivative. And I got my factors, or I like to call them my components. All 4 components here. Followed by my second derivative. And of course, the x is going to be from 0 to e. You know, the domain is from 0 to e. So that's the only thing I draw for my chart in terms of the domain. -1 is always negative. Log of x, and I drew a little graph up here to the top right. Log of x is going to be positive when x is greater than 1 and negative when x is less than 1. Okay, so that's based on the graph of the log function. X squared is always positive, and 1 minus the log of x quantity squared is always going to be positive. And from there, you're able to figure out where the second derivative is positive and where it's negative. I think that's absolutely fascinating. Yes, Rodrigo agrees. Sebastian agrees. Thank you, Nicholas. I mean, you look at what you're able to do now. Look at how you're able to analyze functions using calculus. Okay. In pre-calculus, you wouldn't even deal with a function like this in terms of graph. With calculus, this advanced knowledge, we can use it to help us graph very interesting functions. Okay, so then like for just so the second derivative is positive when x is less than 0. Okay, so how are they getting that? You know, what are they doing there? Well, how are they getting positive for that second derivative when x is between 0 and 1? Based on the chart. Based on the chart here. Okay, I'm looking, Kelvin has a negative times a negative divided by a positive. That's right. You have a negative times a negative divided by a positive times a positive. I'm using parentheses, but you could use multiplication symbols also. And that's going to be positive. Easy. Easy. So, and you can similarly analyze, yes, easy. That's right, Joe. You can similarly get negative here, you know. When the second derivative, when x is between 1 and e, the second derivative is negative. Now, by the way, x equals 1 is an important value because the log of x would equal, gotta be a little bit careful here, one moment. Yeah, the log of x equals, the numerator equals 0 when x is 1. The log of 1 is 0. Okay. And so, okay. Our function is going to be concave up on the interval from 0 to 1, and it will be concave down on the interval from 1 to e. And since concavity changes at x equals 1, the point on the function, the coord with the point 1, f of 1, which is computed to be 1, 0, that is an inflection point. Okay, please let me know if you have any questions. Okay. So we've now talked about concavity, and that's good. We know where this function increases. We know its domain. We know the function's domain. We know where the function increases, where it decreases. Well, we know the function just decreases. We know where the function's concave up, concave down. We have an inflection point. Another question that might be helpful for this is, since the domain is limited, okay, since the domain is between 0 and e, you know, what's going to happen at those endpoints? X equals 0, x equals e. I mean, what intuitively happens there to the function? Well, the function's not defined at those endpoints, so it's possible at the endpoints you could have what? In other words, x equals 0 could be a something. I'll write the word down. I'll give you a hint. Asymptote. Good. Good, Zoe. So we can have asymptotes at those points. Okay. And if we go to the next page, we can actually establish that. Okay. So remember our function, put it in blue here. Our function our function is equal to the log of 1 minus the log of x. So as x approaches 0 from the right, and this would make sense because the domain, remember, the domain of this function is from 0 to e. So we have to approach 0 from the right. As you know, that's what that little plus sign means there. The plus there. As x approaches 0 from the right, 1 minus the log of x would approach infinity. It would. Because the log, what happens to the log function as x gets less and less positive, the log function gets negative. And 1 minus a negative infinity is equal to positive infinity. So therefore, as x approaches 0 from the right, our function has to approach infinity. Because we're taking the log of a function that approaches infinity as x approaches 0 from the right. So what's the log of infinity? That's infinity. So x equals 0 is a vertical asymptote. See, it might look hard to do, but it's not hard to do. Now, on the other hand, what if we approach the exponential function? If we approach the number e, which is about what is e? It's 2.718 and keeps going, right? As we approach e from the left, 1 minus the log of x has to approach 0 because the log of e is 0. No, the log of e is 1. 1 minus 1 is 0. So that means as x approaches 0, I have a typo here. This should be an e. Hold on. We're approaching e from the left. Okay, let me fix that on my paper too. So as we're approaching this number e from the left, the function then, log of 1 minus the log of x, has to be approaching negative infinity. Because if 1 minus the log of x approaches 0, okay, if 1 minus the log of x approaches 0, well, then the log of 0 approaches negative infinity. So you have another vertical asymptote. So what happens is the function as x approaches e from the left, the function is going to go down, an asymptote down. On the other, on the other hand, as we approach 0 from the right, the function's going to asymptote up, goes to infinity. And so now we put all this information together, and we can graph our very interesting function. So I put, of course, the point 1, 0 on the graph. And let me just go from the left asymptote. So here, I'm tracing the function. Is the function concave up or concave down? This part, up to 1, 0. Is our function concave up or concave down? Concave up. So think of like your hand. If you hold your hand, palm of your hand up, that's concave up. Joe, I don't know what's D. I'm still learning text notation. DU. Oh, CU. Okay, I got you. So this is concave up. And then the 1, 0 was an inflection point. What happens to the function after 1, 0? It becomes concave what? Concave down. Okay. And by the way, the function is decreasing over the entire domain. I mean, I think this is just absolutely fascinating that we can graph these interesting new functions using our calculus knowledge. I think it's just really a wonderful thing. And I think many of you like it also. You know, I mean, and of course, not all. Oh, yeah. Let me just. Are there any questions? I'm going to stop the recording. But are there any questions? I'll note here that E is about 2.718. So the 3 on the x-axis is here. So that's why I placed E there. Okay, I'll stop the recording. Are there any other questions before I stop the recording?